So my name is Agustin Majdalani. I'm a research associate at the BRE Center for Fire Safety at the University of Edinburgh. And I will present my current research related to firefighting interventions in basements, or more generally in underventilated compartments. And as Deborah said, I will close with my BRE Trust impact. So a quick overview of the full presentation. I will first explain the background and the purpose behind my current projects, which are 2 or hopefully 3. I will update you on the results obtained after the first and second one. I will present the proposal that we put forward for hopefully getting the third one. And I will close with how the BRE Trust impacted in my professional career. So as firefighters enter an underventilated fire, compartment fire, allowing fresh air into the compartment through the door, there is a risk of a sudden fire development that may come in the form of a rapid flare or a backdraft. In firefighting terms, this would be what they call a smoke explosion. Basically, this means that fires in basements are still an unresolved problem for fire brigades, big concern for them, and also that most of the guidance out there is based on anecdotal evidence following injuries and death. So, therefore, our purpose is to try to understand a little bit better how the fire dynamics in an underventilating compartment behaves, and to try to develop simple guidance for the fire brigade and hopefully influence building regulations and design. So the aim of the first project, the tactical ventilation project, was to find practical ventilation strategies in potential backdraft situations to minimize the impact of this very extreme phenomenon. For that, we used a small-scale elongated box and apparatus, which was meant to replicate real conditions, of course, in a reduced scale in the laboratory. This is the box, the experimental box, the apparatus. It measured 40 centimeters high, 60 wide, and 100, so 1 meter long. It had 3 openings, one at the front, one at the back, and one at the ceiling. And it also had a sill coming down from the ceiling, dividing the box into 2 different compartments: a fire compartment at the front, where we would light the fire, and a smoke compartment at the back, where we would do all the testing. So we designed 2 experimental setups. The first one to reveal the conditions that trigger a flashover in the front compartment and a further backdraft through any of the ventilation openings that we wanted to test, and a second one to find practical actions to deal with that, with the severity of a backdraft. So basically, in short, the first setup was designed to eradicate the likelihood variable, and the second one to deal with that phenomenon. These are the typical results obtained in the fire compartment and in the smoke compartment. I won't go through the details, but basically this shows that we let the fire develop until it reached flashover conditions, so it was fully developed. Then we closed all the ventilation openings, killing the fire. Once the fire was put out, we opened either the ceiling vent or the front door, triggering a backdraft through the ceiling vent or through the front door. So these images show the results after opening the ceiling vent with a backdraft that extended beyond the characteristic length of the box, in this case, the height. So on average, we had flames extending beyond the 40 centimeters. And these other images show the backdraft through the front opening. And again, the flames extended beyond the characteristic length. In this case, is 1 meter. So imagine if you extrapolate this into an urban scale. So once we knew exactly how to trigger a backdraft, so we had the configuration that triggered a backdraft, then we started testing different tactical ventilation strategies to try to find practical actions from the firefighting perspective that would minimize the severity of this phenomenon. After several tests, we found that the imminent severity was significantly reduced by opening a second vent and creating a crossflow through the compartment. So a clear pathway. Instead of opening one, we opened immediately a second one, and the severity went down. So the experimental conclusions of this first project are the following. The pros of single-sided natural venting is that it improves the visibility for the firefighters and reduces the average gas temperatures, but this comes at the expense of fire growth and flashover, a very high risk of a backdraft or a smoke explosion, and the fire extending along the vent route all the way to the facade of the building. However, firefighters can typically deal with a fully developed fire and a fire extending all the way up to the facade, but they definitely cannot deal with a sudden backdraft. However, compared to single vent, the dual opening crossflow natural considerably reduced the risk of the backdraft, the pressure buildup inside the compartment, and the severity of the flare-up. Nevertheless, flare-ups can still occur. So, what are the practical conclusions for the firefighters? First, it is unsafe to vent indiscriminately, just because there are available openings. Availability is not the same as suitability, and although this sounds a little bit silly, there are many recommendations out there from firefighters, tactical ventilation policies, and even regulations to vent just when you have available openings. What means suitability? Well, it would depend on each situation, but for the least, we need two different openings to create a clear crossflow through the fire compartment. This natural crossflow will reduce the pressure buildup, which is actually the background behind this problem, inside the compartment, and will significantly reduce the likelihood, and if it happens, the severity of a backdraft. But what happens when we have a compartment with a single opening, so an unsuitable opening? Well, this question led to the second project, which is the gas cooling technique project. And it says, in situations where there is no room for a ventilation tactic, the gas cooling appears as an effective solution, reducing not only the temperatures, but also the likelihood and the severity of a backdraft. So the key objective of firefighting for the firefighters is not to put down a fire. That's the ultimate goal. Their key objective is to control the environment as they get through into a compartment so that the extinguishing process can be effectively performed and safely achieved. Well, the gas cooling technique controls the environmental conditions inside the compartment, reducing the temperature and the likelihood of either a flashover or a backdraft. So basically, in short, this technique creates a safe approach to and from the fire. So this is how the technique works very quickly. So once inside the compartment, and after closing the door behind them, the branch operator applies pulses to the smoke layer. These pulses extinguish the flaming combustion by cooling, diluting, or inerting. That would depend on each situation, allowing the firefighters to advance up to they get to the fire. The width of spray and the pulse length is adjusted depending on the penetration required to ideally reach the back of the compartment and maximize the heat exchange between the spray, the water spray, and the hot smoke layer. And the compartment size dictates the water spray cone's angle, pulse length, and the number of pulses. For instance, if a firefighter gets into a corridor, it will be just a single pulse. If it gets into just a medium compartment, it would be 3, 1, 2, 3. If it gets into a compartment like this one, it would probably be 5. So the aim of this second project was to analyze when it is effective or otherwise ineffective to apply this technique. These are some of the typical results obtained. These results show that basically the pulsing technique gets better and better, so it is more effective as the thermal conditions increase inside a compartment. So in practical terms, the conclusions for firefighters are, it is effective to apply this technique only when there is sufficient thermal energy. In our experiments, this threshold was found to be around 200 C, but of course, this needs to be validated once we get into real size. Our second conclusion is that the more controlled that be the exercise of the momentum of the spray, of the water spray, by means of adjusting the nozzle, and flux density by means of adjusting also the pulse length and the quantity of pulses, the more the ability to control the overall reliability of this technique. But the gas cooling technique still implies opening a door, therefore there is still a risk of a backdraft, of explosion. So this is where we brought Project 3 and a proposal to investigate this so-called cutting extinguishing technique. This technique is an integrated water abrasive cutting and fire suppression system, which is lodged from the outside of the compartment, so it basically penetrates through any material, technically, and injects water spray at a very high pressure. So the aim of this third project is to investigate at reduced scale at the beginning the potential effectiveness of this technique. So overall, the conclusions and results obtained from these three interrelated projects will hopefully give the firefighters some information for them to put together into simple guidance and tactics, combining the three techniques to fight fires in basements or more generally in under-ventilated compartment fires. Well, now that we've been through the research part of the presentation, I will very quickly summarize what was the BRE Trust impact in my career, and I will try to measure that in terms of opened opportunities and how I took those opportunities and transform them into experiences. Let's see how it works. So the first opportunity that the BRE Trust gave me back in 2010 was a studentship to complete a PhD. I did my PhD in Edinburgh from 2010 until 2014, researching deeply into the concept of the compartment fire framework developed by this man, Philip Thomas, who is regarded as one of BRE's more influential researchers in fire safety. Actually, he's the father of fire safety. And he developed this concept during the 60s and 70s. So I tried to study how this concept, or to what extent his concept was still applicable in contemporary architecture like this one. For that, I had the great opportunity to meet and discuss with some of the top architectural practices in the world, like Pelli, Pignoli, Foster & Partners, Zaha Hadid, and BRK Ingalls, sometimes working with them in a few projects like the ones. So those pictures were from projects that we worked before. So the idea of contacting them and meeting them was to try to define what is a contemporary compartment compared to what Thomas defined 50 years ago. I also had the chance to design, build, and run my own small-scale tests and take all this experience to run this series of large-scale tests that we did at BRE's burn hall in Watford. And these were regarded as, at that time, the most censored tests ever done in fire research. I hope that this record is still in place there. We were a group of around 10 students, research associates and staff, both from the university and from BRE. It was a great experience. Not only I had the resources and the contacts to pursue my PhD, but I also had always the chance to showcase my work like today, getting in turn very valuable feedback from different stakeholders. So I basically was presenting regularly my research to my supervisors at BRE. I also had the chance to present at some point to BRE's board of directors. I presented at a previous BRE Trust conference, and I even had the chance to present to consultants like Arup. All their feedback was great, and it actually influenced a lot on my approach to my thesis. At the end of the PhD period, I also was given the opportunity to travel and settle down in Australia at the University of Queensland to discuss my final conclusions with the team down there and with my supervisor. So for once, try to keep calm and write down the thesis, which I did, luckily. All that experience during my PhD, together with my previous experience on the field, opened me the door to a senior consultancy position, where I had the opportunity to work in a broad range of projects like retail, industrial, bioenergy, and the scary nuclear sector, which was, again, great to try to apply all my concepts that I learned during the PhD. In 2015, I came back to the BRE Center as a research associate to take the position that I'm now holding. And I had the opportunity to exchange once more not only knowledge, but ideas and projects with different, again, stakeholders. I was working together with BRE researchers at the very beginning, with researchers at other universities, with trustees at the Fire Service Research and Training Trust, with the firefighters, and actually that was crucial because this gave birth to my current projects, and even with the research and development departments of private companies, like, for instance, Angus Fire, who are willing to participate in this third project that we proposed. All this extensive experience gifted by the BRE Trust in a direct or indirect way allowed me to become first a member of the Institution of Fire Engineers and then a chartered engineer. So in summary, during my last 6 years, the BRE Trust not only impacted significantly enhancing my professional career, but it also deeply and positively affected my personal life. So, in short, thank you very much to the BRE Trust for all this path and for all this support, and of course to the Fire Service Research and Training Trust for funding my projects. And thank you to all of you for surviving the last presentations.